Here we're going to design a composite beam that's made from steel and red oak. It's going to be bolted together with 3/8 by 5-inch steel bolts that have an allowed shear stress of 1 kip. And our girder beam is designed to carry the central span of a 12-foot by 20-foot balcony using a design load of 100 pounds per square foot. So here we have our 12-foot by 20-foot balcony, and the girder is in the center. We have a design load on this balcony of 100 pounds per square foot. So our area is 12 feet by 20 feet, which would be 240 square feet. The total load will be 100 pounds per square foot times 240 square feet, which will give us 24,000 pounds. So the total weight then, we'll use kips here, it will be 24 kips, which is 1,000 pounds. If there's a support wall here and here, joists are all going this way. The tributary area will be right here, half. So the girder is carrying this half of the floor load. The weight on the beam will be half of the W total, which will be 12 kips. And it'll carry it as a distributed load. So therefore the value of the distributed load will be the total weight on the beam divided by the length of the beam, which will be 12 kips divided by 12 feet, which gives us 1 kip per foot. With that, we can make a quick V&M sketch of the girder, where we'll have a simple support at each end. The length here is 12 feet. We'll call this A and B. A would be down here, and B would be up here. And we have a uniform distributed load of 1 kip per foot distributed on here. And we know that that has an R equivalent of 12 kips. And from the symmetry of this, the support reactions will be 6 kips at each end. From here we can make a V sketch. And we'll start out at 6 kips. We have to immediately begin to offset that support reaction. And we know at the other end will end on 6 kips. And these will connect linearly and that will be the V curve for that load. So we see that V max will be 6 kips, and it happens at either end, and it decreases in the middle. From here, we could also make the M sketch. So this would be M. And recall that the area up here, this is 6 feet to that point, that area is delta M below. So the area is 1/2 6 times 6, which will be 18. That will get us the peak, and we know that we'll get there parabolically. So therefore M max will be 18 kip feet. And with that we have our design loads for this problem. That takes care of our loading that we have acting on the beam. Next, we have to address the fact that that's a composite beam. We have two different materials, steel and wood. And recall, for composite beams, if you have a beam that's bending, it's being bent into some radius of curvature rho, and rho is EI over M. We found that in an earlier chapter on bending, where EI can be called the flexural rigidity, and they act together. That's the material properties, and that's the geometric properties. And what we find then, that materials that have the same EI will bend and behave in the same way. So for a different material, as E goes up, if we reduce its I, it'll have the same flexural rigidity. Well, we can use that to our advantage here. For example, let's say that we had E2, a second material, was 1/2 of E1. Well, then I1, let's assume it's a rectangle of height and base, will be 1/12 BH cubed. And I2 then, if we wanted them to match, would be 2 times I1, which would be 1/12 times 2b h cubed. And if we modify the cross section such that this is our computation for I, it'll have the same flexural rigidity, and we can treat it as the same object. We cannot change h, we can only change the width. If we change h, we would move the neutral axis. If we shift the neutral axis, let's say we doubled it down to here, that changes the value for rho. So as a result, we only change width. And the way we do that is we calculate the ratio of n, which is E1 over E2, the ratio of the modulus of elasticities. And we would have, in this case, E1 over 1/2 of E1, which gives us an n of 2. So our process is to compute the value for n and then change the width by the value of n. So let's apply that to this beam. For our value for n, we'll do as E steel over E wood. And I like to do it with the larger value on top. So we'll have 29 MSI over 1.81 MSI, which works out to be 16. That tells us that we can change the steel, increase width of steel by 16-fold, and the device will then be all wood. So what will our new cross-section look like? If we look, we have 1/4 of an inch width on our steel here. And if we multiply that by 16, this will now be 4 inches wide. And the same for this one, 4 inches wide. So our new modified cross-section will look like this. It'll be 4 inches by 10 inches. The wood will still be the same. That will be 4 inches by 2 inches. This metal plate is now being replaced by wood, and that will be 4 inches by 10 inches. And then on here we have 4 inches, which gives us a grand total of 12 inches across the bottom. What we have here, this is all wood, and its equivalent cross-section. And all of our equations that we use, such as tau is VQ on IT, Q and I are based on this modified cross-section. It's important to note that T here will be the actual thickness of the cut. We also saw in the past that bending stress can be NMC on I, where n is the n that we're calculating here. And here this I is also based on the modified cross-section. If we were looking at deflection formulas, for example, the deflection for a uniform distributed load, it would be 5W L to the fourth on 384 EI. And again, we find our EI is here, and we could do this for the all-wood equivalent composite, where this would be the value calculated from this diagram. So it turns out many of the parameters that we calculate can use a modified cross-section if we're dealing with a composite material. We take our composite material, compute n, and make it a homogeneous cross-section of one of the materials. And then from there we can modify all of our equations to find the limiting values. From here we can calculate I of the entire composite. The neutral axis is here, right down the center, because of the symmetry, which gives us 5 inches here, and this would be 3 inches. We're going to do this as large rectangle minus small rectangle, which will give us 1/12. B is 12 inches, and H is 10 inches, minus the inner rectangle 1/12. B is 4 inches, and H is 6 inches. This will be 1,000 minus 72. So we then find that I will be 928 inches to the fourth. Next we need to find Q. And we need Q for this region right here. Here's our neutral axis, and that's the region beyond the cut. We have to cut it in 2 places in order to free it up. So we need the Q of that region, and recall that Q is the AY bar of that region. So that area is 4 inches by 2 inches, and its Y bar distance would be 3 plus 1, which is 4. So we'll get 32 inches cubed for that. We'll call it Q1 at the top. Now that we've found the geometric data, we can design the bolt spacing for this beam. Recall that Q is VQ on I, which will be 6,000 pounds. That's our kips. Q is 32 inches cubed, divided by 928 inches to the fourth. So we get a shear flow value of 207 pounds per inch along the length of that beam. And recall that Q is also equal to force divided by X along the beam. However, in order to analyze this, we need to cut it here and here to free up this section. And note that we're cutting the bolt in 2 places. So that bolt is in double shear, which means this will be 2F. We have to cut through 2 bolts, divided by X, equal to 207 pounds per. And here's the X that we're looking for. So X will be 2F on Q, which will be 2. The limit for the bolts is 1,000 pounds of shear force, divided by 207 pounds per foot, which will give us 9.7 inches, which we're going to call 9.5 inches, just to make it easier to measure. Someone has to lay this out and drill it, and we could do it 9 3/4, but I'd rather err on the lower side than the upper side. In the long run, it'll be the same number of bolts and the same number of holes anyway. Let's just make it easier for them to lay that out. That's our answer, but let's see what else we can do with this. Let's say we wanted to glue it. Instead, we're going to put glue in here and we'll glue this thing together. Tau, the shear strength required for this glue, be VQ on IT, which is Q over T as well, either one. So we have 207 pounds per foot divided by T. Now T is the thickness of the cut, and this is 2 inches times 2. So that's going to be 4 inches of cut to free that section that we have up here. Right, we need to free that section, which gives us 52 psi, which is actually rather low. Typical like wood glue is approximately 120 psi. So that's an option if we could find glue that works well enough for wood versus steel. The bolts would certainly be better, or we could use both if we wanted to. There's certainly no need in this case. But just a way of looking at what T would be in the case where we need to make 2 cuts to free that segment. So that represents the shear stress on these 2 faces, which by symmetry would also be the same shear stress down here. Let's also check tau max, which we know will occur on the neutral axis. Right here on this axis we'll have our largest value for tau. That's because that's equal to VQ on IT. And that Q will be the Q about the neutral axis. So Q about the neutral axis will be Q1, the one we calculated before for this region. But now we have to add these 2 regions in, which I'll call Q2. So Q2 will be AY bar for these regions here, and there's 2 of them. So it'll be 2 times the area, which will be 4 times 5, times the centroidal distance, which would be 2.5, which gives us 100 inches cubed. So therefore the Q on the neutral axis will be the 32 inches cubed that we had from Q1 plus the 100 inches cubed. So Q on the neutral axis is going to be 132 inches cubed. V we know is 6,000 pounds. It's the maximum shear. Q is the modified section on the neutral axis now, which is 132. I is a constant. It's 928. And here, the value for T must be the actual thickness of the cut. And the actual thickness of the cut is here and here. So T on the neutral axis is 1/4 plus 1/4 is 1/2 of an inch of material that we have to cut. So with our formula for a composite, we always use the actual value of T. So this down here will be 1/2 of an inch. 1706 psi, or 1.7 ksi. And this is in the steel. And the typical yielding stress for steel is about 21 ksi. So this is okay. Since we have all the data, it's not hard to also check this thing for bending stress. Recall bending stress is NMC on I. Well, we already have I. C is the distance to the outermost fiber, which would be 5 inches. M we calculated earlier. M was 18 kip feet. Now we have to fix this. It would be 18,000 pound feet. And there are 12 inches in 1 foot. Make a quick conversion factor. So the moment with the appropriate units here is 216,000 pound inch. or 216 kip inch, whichever one of those you want to use. Let's check this for the wood. So this region right here would be the maximum compressive, and this region down here would be the maximum in tension. They'll both be the same but opposite in sign. So for the wood, we have N, M, C on I, where N is 1 here because that's not a modified section, it is wood. M is 216 kip inch, C is 5 inches, and I is 928 inches to the fourth, and from that we'll get 1.2 KSI. And note that if we run kips in here, we'll get KSIs out here, kips per square inch. And for wood, in compression, we're typically limited to about 7 KSI. So that's okay. And in tension, it's going to be almost double that. It's around 15 KSI. So in tension, it's also going to be okay. Now we could check this for the steel, which is NMC on I. And the steel is the modified section. And notice that this is all the same calculation. And we're looking at this region up here. However, it's in steel. So this will be N times the stress in wood, which will be 16 times 1.2, which gives us 18.6 KSI in the steel. And a typical value for steel is around 36 KSI. So again, we're going to find that that's okay. Another thing that we would need to check for this beam would be the deflection. And typical codes say that the deflection Y, which is how much the beam bends down, has to be less than the length of the beam divided by 240, which is 144 inches long. Remember, it was 12 feet, divided by 240, which is 0.6 inches. And we have a deflection formula for a distributed load. It's Y is equal to -5 little w, the distributed load, L to the fourth, over 384 EI, or that's the E and the I of our cross section. Again, we see those terms. And the value of our distributed load, recall, was 1 kip per foot, which is 1,000 pounds per foot. And 1 foot is 12 inches. So our deflection will be -5 times 1,000 on 12 times 144 to the fourth divided by 384. And the E was 1.81 times 10 to the 6. And the I was 928 inches to the fourth. And here we're going to use the E of wood because we're working with a cross section that's entirely made of wood in this model. This gives us 0.3 inches, which is less than the 0.6 allowed. So again, this is okay by deflection. And there really is one last thing we could check if we wanted to. We could also check the bearing stress. Stress bearing is force per unit area. And what we're talking about here is, here's our beam that we're designing. Here's those wooden blocks. Here's our nice bolts going down the system. There's our 9.5 inch spacing. And down underneath here, we need to support this on a column to carry that load down to the foundation support. So let's assume that that's 4 inches. And let's assume the steel is what's doing all of the bearing. The wood we're not going to rely on at all. So if we look at that, we've got the two 1/4 of an inch pieces of steel, our block of wood, and then it's sitting on whatever this column is. So then the stress and bearing will be 6,000 pounds, that's our V value, divided by the area, which will be 2 times 1/4 times 4 inches, which is how far back that goes right here. That's the area that we're working. So the bearing stress will be 3 KSI. And for steel, we're allowed about 36 KSI typically. So once again, this is also okay. So with that, we've checked quite a few different parameters for this beam. Here's a summary of what we just checked. We found that the bolt spacing could be 9.5 inches. And that's with a force in the bolt at 1,000 pounds. And that would be shear force driving that. We checked the maximum shear stress, horizontal shear stress on the neutral axis, found it to be 1.7. Steel can reach as high as 20, so that's okay. We checked the compressive stress in bending of the wood fibers at the top here along the top edge of the beam. We found that at 1.2 KSI. 7 is allowed, so that was okay. We also checked that same criteria for the steel. We found that that was okay. We checked our deflection criteria for code, and that was okay. And we went as far as to check a typical 4-inch bearing support, and we found that that's also going to be okay. Thanks for watching.